Find dy dx, given that y equals integral 0 to x cubed of cosine of t squared dt. Okay, so this is a fundamental theorem calculus question. So the way I usually handle these is I'll be like, all right, I'm going to say g of x. That is g of x right there. We want to find the derivative of this whole sum right there. And so I'm going to start by rewriting this as big G, the integral of such, of x cubed minus big G of 0. Where big G of 0 is just the integral evaluated at 0. And that is just going to give us a constant. So when we want to find the derivative of these, because we want to find the derivative of the whole thing, and since they're separated by a minus sign, we can just take the derivative of each. The derivative of a constant in this case will be 0, just because a constant's just, 2 or 3 or 12 or whatnot. And so we take the derivative of 12, it's just going to go to 0. Now the derivative of big G of x cubed will be the derivative of x cubed times the derivative of the interior, which will be 3x squared, the derivative of x cubed. This right here is the chain rule. This is going to be kind of confusing because the notation will look similar, but sidebar. We have f of g of x, which is a nested function, if you will. Take the derivative of such, and this uses the chain rule. So it'll be f prime of g of x times g prime of x. And that's what we're doing here. So to take the derivative of big G, we get small g. I guess I can get rid of that derivative sign. Whoop. We have of x cubed, and then multiply by the derivative of the interior, which is 3x squared. And that's what we did right here. So then this will then be dy dx. But we can go a little bit further because we know what g of x is. G of x is cosine of t squared. So this would be cosine of x cubed squared times 3x squared, which would then give us, simplifying things slightly, so still being terribly complicated, we would have dy dx equals cosine of x to the 6 times 3x squared. And that's how I approach all of these fundamental theorem of calculus questions. Now your thought process might be like, whoa, wait a sec, can't we just take this x cubed, plug it in for t, and then multiply by the derivative of the x cubed part? Yeah, you absolutely could, and that would work in this situation. It might be a little bit more complicated if you have x in the top and the bottom, but it would still be the same principle. We're basically just using the chain rule here. The real meat and potatoes, the value of the fundamental theorem of calculus, is the fact that we can say this. Everything else that we did after that, that's just it's small potatoes. But like for us, it's useful. This is the big, heavy-hitting power associated with fundamental theorem of calculus. This right here is why the fundamental theorem of calculus is so famous. So well-renowned, so powerful, so useful, so much filled with utility. But if you've done a handful of integrals already and finding area under the curve, this feels familiar and comfortable to you. So that's why a lot of math books will make a big deal about this, but you really don't understand. It's like, why is this such a big deal? This is why. So this is how you do the problems. You'd have your equation, you have your x's, you have your dummy variable. You rewrite it in terms of, I like to do it, if I can, I like to use g of x. You write it as in form of big G of x. In this case, it's big G of x cubed minus big G of 0. And you know that the integral of g of x here with respect of 0 will just give you a constant. And so that goes away. You go back down and you basically solve it and you use the chain rule and you get an answer. Ooh, I should probably check to see if this answer is even possible. Is it an answer? Am I completely wrong? Maybe. Nope, maybe. Cosine of x 6. Ooh, why is there a... Nope. Aha, this one, top one. So, this would be the answer. That's how this problem is approached. And I will see you guys on the next problem. Hope this helped.